Thanks a lot. Thanks a lot for the organizers for allowing me to give this talk. Okay. So, my talk will be on some salient features of Indian astronomy. Yeah. So, as you might have heard, there are very many references to sun, moon, stars, earth, planets, meteors, etc., even eclipses in the Vedic period. And observation of stars are necessary for performing the rites at the correct time. And names of many stars are mentioned. The spherical nature of Earth is implicit in many statements in Rig Veda. So there are several references to eclipses. So there are references to Swarabhanu, the Asuras taking the sun with darkness. And it is mentioned that family members of sage Atri were well versed in understanding eclipses. And then the concept of nakshatras was there, which is somewhat unique to India. Rather, it began in India and they traveled to China and Arabia also later. See, this is because the moon's sidereal period is close to 27.11 days. So that is, the moon covers nearly 1/27 part of the ecliptic per day, okay, in its circuit in space, okay, in the background of stars. So that is why it was found natural to divide ecliptic into 27 equal divisions called nakshatra. So each day is associated with a nakshatra. And here, please note that ecliptic is the ecliptic zodiac you will keep hearing. So that is some zodiac is an imaginary belt, okay, in the stellar background among the stars, which is a circle, a belt, circular belt. And ecliptic is a circle in that, in the center of it, let us say. So that is where the sun moves as perceived by us. As perceived by a person on the earth, the sun is moving in the background of stars. I will come to that, explain it a little later. So that path is the ecliptic, and most of the planets and moon also are very close to this ecliptic. We all of us know this concept: day, month, and year. Okay, so these are the three clear time markers as even casual observations of the sky reveal. Okay, so day is the time interval between successive sunrises, and month is the time interval between successive new moons or full moons, and year is the time required for the sun to complete one circuit around the earth in the background of stars. But it is from a geocentric point of view, it is perfectly valid to say that the sun is moving around the earth in the background of stars. And how long does it take to complete one circuit? So that is the year. Now, all major civilizations grappled with them and the correlations among them. So now we have to distinguish between two things: daily motion of objects. So we see it as a hemisphere, okay? Inside of a hemisphere, and the path taken by any object is called a diurnal path. Okay, so like sun, moon, or planet, or any other object. Okay, so that is called a diurnal path. So that object will rise in the eastern portion of the sky, go up, okay, and then come down. It will go in a slanted path, and that path is parallel to the equator. Our equator, our Earth's equator, and that is indicated by the circle which is connecting E and W. See, E and W, you see. So that is the circle that's called the equator, celestial equator, which is parallel to the Earth's equator, and the path of any object is parallel to that. That is called the diurnal path. Okay, and so this is the daily motion we see. Apart from that, we see that the sun, the object moves in the background of stars. The stars are fixed with respect to each other. Okay, of course, that is also, see, nothing is absolutely certain in astronomy. Even stars have some small motion, but that is a modern thing which we are not. That is only small. One can take for all practical purposes. All stars are fixed with respect to each other. There is one fixed frame in which an object moves. So that is the motion in the background of stars. So now, this is how the Rig Veda explains a year. Dvadasharam nahi tajjaraya vavarti chakram paridhyam rutasya aputra agne vichinaso atra saptashatani vimchatischa tastuhu. The wheel of time formed with 12 spokes revolves around the heavens without wearing out. O Agni, on it are 720 suns. Okay? Saptashatani vimshati. Okay? So that is a verse in Rigveda. So there, it is as if the year has 12 months. Okay, Dvadasha, you see, Dvadasharam, 12 months and 360 days, right? Because 720 days and nights, so 360 days. So this is, of course, 5 or even 5.25 days are added later. Okay, this is only the original, much earlier. So the now months or seasons are discussed in Taittiriya Samhita, part of the Vedic purpose. So there are 6 seasons and each has 2 months. Madhu, Madhava, constituting Vasanta Rutu, Shukra, Shuchi, Grishma, Nabas, Nabasya, Varsha, Isha, Urja, Sharad, Sahas, Sahasya, Hemanta, and Tapas, Tapasya, Shishira. So these are the 12 months and 6 seasons. And concept of Adhikamasa is already there. Mention of 2 more months than the 12, okay, called Samsaspa and Amhaspati. See, this is because that aligned lunar months and solar year. Lunar month, I already mentioned the definition, but it is not something fixed. New moon to new moon or full moon to full moon. It keeps varying, even from sometimes it may be as low as 28, sometimes it may be 30, but average is around 29.5 days. Okay? And so 12 lunar months constitute 354 days, whereas a year has 365 days. So to align the lunar months and solar year, one additional month has to be added sometime. That is the Adhikamasa. Even now we follow it. Even now the concept is same, though the calculations are more accurate. Taittiriya Samhita also observes Tasmat Aditya Shanmaso Dakshine Naiti Shad Uttarena. Thus the sun moves southwards for 6 months and northwards for 6 months. And the equinoctial day Vishuvat is also mentioned in Taittiriya Brahmana. So now, what he means is the following, okay, what the Samhitakara saying is the following. You imagine the earth here at the center, okay, earth's axis is there, perpendicular to the equator and celestial equator. It's a large circle in space, okay, parallel to equator, and sun moves in a circle which is inclined to that, okay. So, and it moves north of, it goes a northern motion, okay. From a southern point, it is going up north, okay, for 6 months, and 6 months it is coming down, okay. So, these are ayana, called ayana. See? So, 6 months northern motion, and that is what is meant, okay. The southernmost point is called winter solstice, and the northernmost point is called northern solstice. But they are not saying that here, but the picture is there. 6 months upwards and 6 months downwards. And the intersection points are the equinoxes, okay, are Vishuvat in India. Okay. So now, all these Vedic descriptions, they are mostly descriptions, qualitative descriptions. There are no numbers, okay, and there are no mathematical treatment. The first kind of mathematical treatment is attempted in what is known as Vedanga Jyotisha. You all, most of you would be knowing that Vedangas are, somewhat adjuncts to Vedas, right? So Vyakarana, Shiksha, Nirukta, and Jyotisha is also one of them. And there's one Vedanga Jyotisha. So here it is mentioned that it is by Lagada, and I will come to that, ascribed to Lagada. It comes in both Rugga and Yajur versions, and it is ascribed to between 1370 BC and 1150 BC. We will come to why it was decided, we will say. So here, the 5-year Yuga cycle is also there in Taittiriya and Vajrayana Samhita, okay? And there are rudiments of a calendar with intercalary months and 27 nakshatras, okay? But there are no calculative, definitive, quantitative statements. In your Vedanga Jyotisha we have, okay? So he says in the one of the beginning verses, Swarakramete Somarko Yada Sarkam Savasavav Syat Tadadi Yuga Magaha Tapa Shukla Ayana Hidak. You see, so when the sun and moon occupy the same region of zodiac, together with the asterism of Vasava, Sravishta, the Vasava is same as Sravishta, and it is identified with star Delphini. So at that time begins the Yuga. And the synodic month of Magha, okay, Magha is there, okay. Then the synodic month is same as lunar month, okay. Solar month called Tapas. The bright fortnight called Magha, and the northward coast Uttarayana. You see, so this compact way how it is put, you see, that is characteristic of all Indian texts much later also. See, that's one of the important things. You see, Indians never leave their tradition. See, always they retain it in some form or the other. So it is evolved. So, in fact, the aim of this talk is to see how the evolution takes place and how continuity and tradition both are there in the Indian text. So, as I told, if it is winter solstice in Savishta, then there is a phenomenon called precession of equinoxes. I will not go into that now. So, when that winter solstice is there in Delphini, then the year would be around between 1370 and 1150. Okay, might have been written a little later. So this is what most Indian astronomy scholars say, and of course, Westerners say no, it's much later. So they say 500 BC. Anyway, it is certainly much earlier than 500 BC. Let us not get into that. Okay, but most of us feel that it is around 1250 BC years. See, Yuga concept is already mentioned here. The whole calendar is summarized there. Tishat Taknam Sashat Shashtirabdaha Shat Chartavoine Masad Vadaja Sauraha Suyetat Panchagunam Yugam Savanendustru Masanam Shashtis Saika Disaptika Yutrimshas Savana Sardaha Surya Strunasa Pajayaha. 366 days form the solar year. In the year, there are 6 Rutus and 2 Ayanas. You see? Charta, okay, Ayana, okay, and 2 Ayana, Ayane, Masa Dvadasha, okay, the 12 solar months, okay, and then Panchagunam Yugam, 5 years make a Yuga, and Sayanendus to Masanam Shasti Seika, you see, Eka B Saptika, add 1 to 60, so 61, so that is the number of Savana months, okay, and 62 is the lunar months, and 67 is the sidereal months. Okay, so that is the moon for go in the circle in the background of charts. Lunar month is new moon to new moon or full moon to full moon, and there is this Savana month. Okay, which is it contains 30 days, some kind of artificial unit, and this plus half 30 and a half make a solar month. The solar month is roughly the time taken by the sun and the average to cover one zodiacal sign, one Rashi. Okay, so that is the and 60 solar months in one Yuga. Okay, so that is the concept here. Okay, see how everything is kept compactly here. The same kind of thing happens in Siddhanta text, but it is much more. Yuga is a different connotation, but the concept is essentially the same. See, everything returns back to its same place. See, that is the underlying concept. In India, that is the thing, right? Everything will be thought has a beginning, then there will be some expansion, and then come back to the original position. But here the short cycle is used. Later we will say that a very long cycle is used. So Vedanga Jyotisha consists of 60 solar months, 62 lunar months, 67 solar months, and 60 into 30 and a half, so 1830 days. So in the sidereal year is 1830 by 5, 366 days, which is slightly more than actual, which is 65.2564 days. So these are sidereal year. The actual sidereal is this, okay? Actual tropical year is little less. Tropical year is 365.2462. That's the tropical year. So that is what is considered in modern times. Okay, this is the sidereal year. But even then, this is slightly more in this. The lunar month is 29.516, which is slightly less than the actual average. And sidereal month is 27.301, actually 27.32. So there are 60 solar months and 62 lunar months in 5 years. So 2 Adhika Masas are there. So 3 lunar years with 12 months and 2 lunar years with 13 months. And here clearly Tithi as a division of the motion of the sun moon, which is relative motion, that is good. Tithi is 1/30th of a lunar month. In one lunar month, the angle between sun and moon increases by 360 degrees. 1/30th of that, that is the time taken for it to increase by 12 degrees, that's called a Tithi. And 15 Tithis in each Parva, it is half a lunar. So very important thing is Vedanga Jyotisha, it is in sutra format. It is a very algorithmic, in algorithmic format. You have to just remember that and then you are through. But understanding will be, I will come to that. Understanding will be in commentaries or explanation by acharyas and so on. So now in this, the short algorithm for finding Tithi, Nakshatra, sun's position in sky, etc. So Vedanga Jyotisha is the first text in India to do mathematical algorithms in astronomy. Okay, there's nothing on planetary motion in this work. Okay, so the sutra format, many of you would be knowing already. The sutra format is there in other disciplines also. Chandas Sutra by Pingala, right? Chandas, the metrical prosody. So then you have the Vyakarana, Padini Sastadhyayi, that is in sutra format. So sutra format is there in all the disciplines in India. And so this is the Vedanga Jyotisha Sutras. The sidereal year of 366 days is too long. But even earlier in Taittiriya Samhita and all that, there is a clear mention of Savana year of 360 increased by 5 days, or lunar year of 364 days increased by 11 days. So maybe 365 days. There is also a mention of a cycle of 4 years with 1461 days, implying a sidereal year of 364.2 days. Okay, and also simple observations would reveal that sun and moon would not come back to the same point at the same time after 1830 days. See, that is a assumption in this sutra, Vedanga Jyotisha Sutra. So even then, they would have, and it will be even then. Even with negative observation, they would have noticed it that it will not come back after this. See, so it is only slightly less actually. Okay. So why does Vedanga Jyotisha have a 366 days sidereal year? So according to one of the scholars, Kupanna Shastri, it was meant primarily to provide a civil calendar whose convenience of division and ease of calculation is important. And difference from actually anyway, because there are only mean motions of sun, moon are considered. Certainly, corrections should be introduced to obtain tolerable positions of sun and moon. So probably there was so many intercalary months were not dropped in Yuga. Okay, the dropping of 2 intercalary months in 13 Yuga. It's not uniformly 2 intercalary months and Adhika Masas in a Yuga, something less than that in 30 Yugas, okay, 13 Yugas. So 13 Yugas will not have 62 lunar months each Yuga, 13 into 62, but minus 2 lunar months, okay. So that is about 23742 days that will come to that. Then you will get the correct value. But this is just an analysis. I don't know really. Yeah. So I can only say that typical of Indian astronomy, the way they deal with it, they always introduce something and they introduce some corrections later. So it is possible. Only a possibility is there. The variation of daytime over the year, okay, the duration of daytime, that is time interval between sunrise and sunset, varies over the year, depending upon the position of the sun on the ecliptic and also latitude of place. Okay. So at equator like Sri Lanka and we venture near these things, near that. So the sunrise to sunset will always be nearly 12 hours or 30 gatikas, most of the year, throughout the year. Whereas if you have northern latitude, if you go to Delhi or something like that, you would have very clearly seen, observed, that in summer the sun set is, happens only around 7 o'clock or something like that. And sunrise will happen in 5 o'clock. Okay, so there will be nearly 14 hours. So like that, it depends upon the latitude. And if you go to, northern, many of you would have gone to, Europe and more northern latitudes, will know that, sun will be there even at 9 o'clock in the night. See, that is because of the, nature of the sun's orbits every year, every day, diurnal path. So this circle EW, that is the equator. So then one circle which is the northern declination. If it is north of that, so then it will have more. The duration, it will be more than half the circle will be here, visible part of the celestial sphere. Okay. Whereas if it is southern declination, it is less than half the circle will be. So because of that, the daytime, that is sunrise to sunset, will be less than 12 hours or 15 muhurtas or 30 gatikas. Okay. So this is a sutra in Vedanga Jyotisha regarding this. The number of days which have elapsed in the northward course of the sun, Uttarayana, or the remaining days in the southward course, Dakshinayana, doubled and divided by 61 plus 12 is the daytime in muhurtas of the daytime. Okay, and the duration of the daytime is 12 plus 2n by 61 muhurtas. Basically, muhurta, as I told you, it is 30 muhurtas make a day. Okay, nearly is 48 minutes. Okay, so where here n denotes the number of days elapsed after the winter solstice, when the sun's course is northward, and number of days yet to elapse before the winter solstice, when the sun's course is southward. On winter solstice, n is 0 and dt is 12 muhurtas. At the equinox, it is 91.5 and dt is 15 muhurtas. That is half of 30. Okay, that is when the sun is on the equator. Okay, at the intersection point. Okay, and then at the summer, it will be 80. Okay, so n will be 183. Next slide, please. So this can be plotted it will be a straight line. Okay, so in this, the straight line is a Vedanga Jyotisha formula. Okay, for the year from winter solstice to summer solstice, the number of days. Okay, so that will be having this form, straight line. And I have also plotted modern formula for latitudes 27 degrees, 29 degrees. They are these curved things. And something which is 35 degrees, it is somewhat deviation from that. So it appears that the Vedanga Jyotisha formula appears to be based on observations at some location with latitude between 27 and 29. Okay, so that is the conclusion. One of the first to analyze this was one Japanese historian of astronomy called Wahashi. So he said that, earlier there's one Pingree who was a high priest of history astronomy and somewhat prejudiced against India. So he said, no, it is borrowed from Babylonia. For everything he will say borrowed from Babylonia. And because in Babylonian 35 degree north, the 12 and 18 match. But that is only 2 days. Most of these days, it is correct for latitude between 27 and 29. So certainly what Wahashi's conclusion is, more reasonable. So this is the sutra. So Aryabhatiya and Siddhantic tradition. So Aryabhatiya is the first available text. Certainly there are more, Siddhanta texts, many earlier Siddhanta texts, maybe from about 1st century CE, Common Era. Okay, so the 18 Siddhantas are mentioned by various later historians of later astronomers, Indian astronomers, in the later centuries. But it is more available. The full text is available, so that it can be considered as the beginning of Siddhantic tradition in India. It has only 121 stanzas and has 4 parts: Gitika Pada, Ganita Pada, Kalakriya Pada, and Gola Pada. You might have heard about this, but nice to hear again. Gitika Pada has only 13 stanzas. It introduces the concept of Mahayuga, 43,20,000 years. And this gives a revolution numbers of planets and parameters associated with them in this many years. Ganita Pada has 33 stanzas. There are very many mathematical problems in that, especially introduction of trigonometry, methods of finding the sine function and all that. And Kalakriya Pada has 25 stanzas, reckoning of time, calendrical concepts, planetary models, epic cycle and eccentric cycle theories, explicit calculation for procedures for calculation of planetary orbits, etc. And Gola Pada has 50 stanzas in problems of spherical astronomy. So it talks about Bhagola, so is Earth is a sphere, and it's also Bhagola, of course, is the celestial sphere. Bhugola is Earth sphere, and different latitudes, how it is seen, if you say. Diurnal problems associated with sun, moon, planets on the celestial sphere, situation of Earth and its shape, brightness, darkness of planets, parallax, lunar eclipses, solar eclipses, and so on. Some of the remarkable features of Aryabhatiya is spherical nature of Earth is very clearly mentioned, and value of pi correct to 4 decimal places is there. Okay, so it says that for a circle of diameter 20,000 units, the circumference is 62,832 units. So the ratio is 3.1146. That is pi. So it's correct to 4 decimal places. And rotation of the Earth is mentioned for the first time, anywhere maybe. Okay. So he says that that just as a boatman, person in a boat, sees objects on the bank, moving backwards, but actually it is the boat which is moving forward and not the objects on the bank. So similarly, we see that the stars and all that, they are all moving, from east to west, but actually it is the Earth which is rotating from west to east. So above all, of course, mathematical theory of motion of planets, eclipses, etc., accurate. And in this, trigonometry plays a crucial role, as we will see. Next slide, please. So these are planetary revolutions in a Mahayuga. So here from now onwards is the concept of Mahayuga, 43,20,000 years. And later, of course, some people talk of Kalpa, which is 1,000 Yuga, Mahayuga. But here it is one Mahayuga, 43 lakh. And the number of revolutions of planets is given here for Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. Also moons, apogee and nodes. One can calculate the sidereal periods from that. This is Yuga Samana Dina, the number of days in the Yuga, civil days. And one can find out the various sidereal periods. Remarkably, they are closer. But how did they get these values? See, this is a matter of lot of investigation. Partially, it might have got from somewhere, or it might have been observational data. In fact, a lot of things need to be studied. One professor, R.N. Iyengar in Bangalore, he is studying, the earlier Parashara Tantra, Urga Garga Jyotisha, and so on and so on. There is some thing about motion of planets. So possibly there is some way of having these numbers in India, but we don't know clearly. But it may be borrowed from Babylonian Greek sources. We don't know. So major astronomers text after Aryabhatiya, Varahamihira, you heard of the famous work Pancha Siddhantika, where he summarizes 5 texts, 5 these things. And Bhaskara 1, Aryabhatiya is extremely cryptic, very, very, concise. So one can just mug up the formula, one can't understand. So explanations are given in Aryabhatiya Bhashya. And also he his own independent work called Mahabhaskari. So this is Bhaskara 1. Then Brahmagupta, the great astronomer, mathematician Brahmagupta, 7th century. His main work is Brahmasputa Siddhanta. And also has written a work called Khandakadya. So they were translated into Arabic even around 8th century, 9th century kind of a thing. Then Lalla, then Shishyadi Vruddhika Tantra, then Manjulacharya, who worked an important work called Laghu Manasa, then Sripati Siddhanta Shekhara, Bhaskaracharya Siddhanta Shiromani, which is one commentary, which has two parts. Okay, so that is the Grahaganita and Goladhyaya. They are mathematical texts purely, whereas this is purely astronomy. So probably Siddhanta Shiromani is these two parts, Grahaganita and Goladhyaya. Leelavati and Bijaganita, of course, also by Bhaskara, and of course very important. But they are different mathematical texts. Then after Bhaskara too, the important developments in Kerala School of Astronomy and Mathematics, Madhava, Parameshwara, Neelakanta Somayaji, Jest Tantra Sangraha Aryabhatiya Bhashya. You might have heard some parts of it. I think I heard Mahesha mentioning Aryabhatiya Bhashya of Neelakanta, I think. Then Jeshta Deva Ganita Yukti Bhashya. These are the major figures. There are many others, Achyuta Pisharadi and Udumana Somayaji and so on. So these are the major figures. So it has infinite series for pi and sine and cosine functions, much before the subject developed in Europe. And Neelakanta Somayaji carried out a major revision of planetary theory, not CC, 1500 CE, where he proposed a Tycho-Brahe kind of model before the heliocentric model of Copernicus. Because here Earth is not moving, it is a geocentric model. All the planets are going around the Sun and Sun is orbiting the Earth. And of course, you would have heard of Surya Siddhanta, a modern version which is very popular even now, probably composed in 10th or 11th century. This is a very extremely popular text which is followed throughout the country, throughout India. You see, people, even now it is taught in various Jyotisha departments where traditional astronomy is taught. You see, so traditional astronomy, wherever it is taught, like in Benares or Tirupati or Delhi, you see the Sanskrit Vidyapitas, the Surya Siddhanta and Bhaskaracharya Siddhanta Shiromani, they are the most important things. So we let these the chapters contained in a typical Indian text, Madhyamadhikara, mean longitude. So suppose the planet is moving with a constant rate of motion, so then you can calculate its position called Madhyama Graha, the mean planet, not a physical things. And if we know the number of days from the epoch, then we can find out its mean position. Then Spashtadhikara, Spashta, do two longitudes. So you have to introduce some correction, I am coming to that. Then Trip Prashnadhikara, three pranas are Dik, Desha and Kala. And it requires, deals with various diurnal problems such as finding north-south directions, latitude of a place, sun's diurnal path, declination, sunrise, sunset times, measurement of time from shadow, relations among various celestial coordinates, calculation of lagna, and so on. They are all discussed in this chapter. I will introduce some other things at least in this lecture. So next slide 17, please. So then, of course, the eclipses, Chandra Grahanadhikara, Surya Grahanadhikara, lunar eclipses and solar eclipses. So include timings, duration of eclipses, duration of totality, magnitude of eclipse, all these are there. I mean, calculations are given. So all these depend very sensitively on parameters associated with sun and moon. And Indian astronomers periodically revise these after observing eclipse. So that is evident by the way they have changed the parameters in the text when they Bhaganas, you see, the revolution numbers or the number of civil days, Yugasavana Dina, that changes, you see, that is probably based on some observations. And eclipses, one can make some clear-cut observations. So there will be separate chapters on instruments for measuring time, illustrating celestial globe, etc. Entradhikara. Okay. There will be expositions on the mathematics used in the text, especially spherical trigonometry. See, this is, we have already seen it in Aryabhatiya had this, Ganita Pada. Brahmasputta Siddhanta has 2 chapters in astronomy, Ganitadhyaya and Puttakadhyaya. Okay, so like that, there may be very different topic books have this. And Goladhyaya will be there, so spherical trigonometry problem. Now the Indian astronomy texts are algorithmic. So commentaries of the text give detailed explanations and very important to understand the verses. And there has been a continuous tradition of astronomy from Vedic times. There have been many innovations in techniques and evolution of ideas in this tradition over centuries. So actually, this, because the way it is projected, it looks like an anda, egg, but actually it is circle. Okay, it is called a eccentric circle. Okay, so now what is happening is, O is the center of Earth, observer is there, and gamma is some reference star. Okay, the Meshadi it is called. Okay, and C is the point at distance OC is equal to small arc from O in direction of what is known as an apogee. So the planets move uniformly in a circle of radius R, capital R, which centered at C, not at O. Okay. The longitude with respect to C, that is theta 0 is gamma Cp, so that goes uniformly, varies uniformly. True longitude is gamma OP, theta. Okay. So theta 0 and theta. And if longitude of apogee, that is gamma apogee, is theta A, then m is equal to theta 0 minus, is called anomaly or Manda Kendra in Indian astronomy. And this distance between O and P, that is called Karna. It is called Manda Karna here, so that has got this kind of a expression. So now that delta theta be theta 0 minus theta. See, theta 0 is this, theta is this. So delta theta difference. So then one can show that k sin delta theta is r sin m. So theta is equal to theta 0 minus this. So you see, trigonometry is needed for finding the true longitudes of planets. That's what I wanted to say. Even if you don't bother about the details, see, trigonometry is needed. You see, now to find a true position, theta. So this is what we have to find. And trigonometric concepts are introduced. So I'll come to that how they are introduced in India. So when this is small, this r by k, r by r is small, so then it is only sine inverse, you can, sine inverse theta is sine theta. This is only to emphasize that the trigonometry is needed for dealing with non-uniform motion. So now I'll introduce the concept of Indian Jya, okay, but have been introduced, but anyway, to make it self-contained, this lecture I'm telling it again. So this is the circle, left side is a circumference of 360 degrees at 21,600 minutes. And the radius is 21,600 by 2 pi. So it is very close to 3438. It's called Trijya. So then for an angle theta or r cos theta, Jya of Jiva is AB is equal to r sin theta. You see, our usual sign, modern sign, multiplied by r. So that is Jya or Jiva. And OB is called Potijya. Pojja. And BD, this portion, that's called Uttamajja, r into 1 minus 1. Worst star sign or Shara it's called. Whereas Greeks dealt with chords, So suppose this is the, arc, okay? Then draw the line between these 2 points. That is a chord, okay? And chord of 2 theta. So that's how they used to consider. Okay? It is like that. You see, one arc, and then suppose that angle is 2 theta, then this line is called chord, and that is 2r sin theta. See, this is theta, half of that. So this is So that way, sometimes in India, earlier it used to be called Jarja. Then later words, that is called Ja itself. Okay. Now, the Indian sign is perfectly suited for writing formula and performing calculations. And chord is far less. So that's the important thing, chord is far less important. So modern sign is very close to Indian Ja, not the Greek chord. So that we have to see. The sine and cosine can be traced to India. See, Ja is also called Jiva. It is adopted by the Arabs. So Jiva becomes Jiba in Arabic is written Jaib. Even though here Jaib is pocket. So Jaib is pocket or fold. Translated into Latin as sinus. Sinus, okay, sine. So the term sine is derived from Indian Jiva. So it doesn't sound like that, but it is how it is. The India, the complement of Ja is Kotija. So the complement of sine is cosine. So ko is definitely Indian origin. See, Ja and Kotija. So sine and cosine. This is how it traveled. Okay, next slide, please, 21. So now with this, when we are armed with this Ja, so then we can calculate various things. So the duration of daytime in Vedanga Jyotisha. Remember, I had talked about it. 12 plus 2n by 61, etc. Right? Days where n is the number of days. That is the number of muhurtas in a day, where this n is the number of days after winter solstice. Okay. So now India later use the formula directly. Duration of daytime is 2 into 15 plus or minus 1 by 6 delta alpha in Gatikas. Okay, Gatika is 60 Gatikas make 1 day. Okay. So Gatikas correspond to how much will it be? So how many 360 degrees? So that is 60. So each Gatika corresponds to 6 degrees, right? So that is how it is. So 15 plus 1 by 6 delta alpha, where delta alpha is degrees. So delta alpha is this. Where delta is the magnitude of declination. You see where the sun is, the distance of the sun from the equator. That is the declination, northern or southern. So delta alpha is this. But delta is magnitude of declination. So you have to add in the northern and subtract in southern. So this is given in Indian text from Aryabhatiya onwards. And this is phi is the latitude of the place. So the important thing is use a formula for the daytime. So in the Greek tradition, there is no such formula. They have got tables. One has to struggle with tables to find out the duration of daytime, sunrise to sunset on any day, for any latitude or sun's declination in the Greek tradition. You see, there is no formula. So that is something unique to India, and this is this formula based. The formulas are directly given because the sign is perfectly suitable for that. Most of the formula will involve sine function, cosine function, and all that. And sine inverse is called or. Or suppose you are given the Ja, okay. So the or corresponding to that called Chapa or Dhanu. So one has to find these things. So clear-cut formula are given for this. It doesn't look like this. What they say is, I will tell you how it says. The Chara is called Chara. They say that find out the Akshajya. Akshajya is or sine phi, where phi is relative to the place. Then say Krantijya, then or sine delta. Okay, multiply them. Divide by the Jujya, the or cos delta. Okay, so that is called Chitijya. Okay, that is divided by Lambajya, cos phi. You see, or sine and sine phi, Akshajya into or sine delta. So that is Krantijya divided by Lambajya or cos phi. So that's called Chitijya. Further divide by or cos delta. So that is called Charajya. Okay, Charajya, and arc of the Dhanu of that is the Chara, and that you have to add and subtract this 15. See, 1/6 of that to get the duration of it. In fact, when phi is 90 minus delta, one can say that delta alpha sine inverse 1 it becomes. You see, because sine phi will be cos delta, cos phi will be sine delta. Cancel. And sine inverse 1 90 degrees. And duration of daytime will be 60 Gatika. Sun never sets. So it will become circumpolar, and that's what happens in northern latitudes. For if phi is greater than 90 minus delta, then this will be greater than 1 actually, and so it will be, yes, sun will never set. It's called the circumpolar. So all this is explained in commentary of texts like Vasana Bhashya, Siddhanta Shiromani. Yeah. So now let us go how the evolution takes place. So relation between time and shadow in Arthashastra. Even Arthashastra has some part on astronomy. Okay, some verses dealing with astronomy. So in one of the verses it says that gnomon is a vertical stick. You see, and it casts the shadow. From the shadow, one can find out time. So suppose the gnomon has a length of 1 Paurusha. So when the shadow of the gnomon is 8 Purushas, 1/18th part of day is passed, 6 Paurushas, 1/14th is passed, etc., etc. So this is the formula he is giving, Arthashastra. Okay. So this is not true for every day. It is true for shadow of summer solstice. At the summer solstice, this is true for a latitude of around 23.7 degrees. So you can see this is the comparison between what is obtained from this formula in or the algorithm in Arthashastra and the actual. Okay. So this is of course not very accurate and only for a particular day, like 23. Yeah. So now there's a better thing in Panchasiddhantika chapter 4. Chayarki Nadibir Dinamanam Shadagna Madbuddhare Tatra Labdam Dvadashahinam Madhyana Chayaya Sahitam. Multiply the daytime by 6 and divide by the daytime for which the shadow is sought. Add the daytime shadow. The shadow of gnomon of 12 units cast by the sun is got. So suppose D is the total daytime and T is the time for which the shadow is sought. Okay. So then D by 2T is this S minus S prime by D. The rest is the shadow at that time. S prime is the midday shadow, okay? And G is the length of the gnome. Okay? So it is better than previous formula, but still approximate. But later in the same text, exact relation is given. Next slide, please. Slide 24. Okay. So now even Aryabhatiya gives the exact relation between time and shadow. Okay. The sutra it gives, and commentary by Bhaskara one explains it. But Brahmasputra Siddhanta gives a more detail in topics. It gives on shadow. So I'm referring to this. So he says, Vritasheshalpasyanya Somyatera Samya. Samya Itara Golayoho Terardena Unadikasya Jiva Saho Rata Sangunita, etc. Okay. So our sign of time elapsed or 2 elapsed from the chara is subtracted from which chara is subtracted, etc. I'll come to the next slide and tell you what it means. Yeah. So it can be explained using this figure. I hope you can not done that well, but still, see, this is the diagonal circle. S or ST is the rising setting line of the sun. Okay, circle. Sun goes up. So this is corresponding to the time to follow, time to elapse. Okay? So that is psi, STC S bar. Of circle between P and W. So that is the chara. Okay. Psi minus chi, that is called theta. So that is 90 degrees minus hour angle. Hour angle is how much time sun has taken after the meridian transit. That is when it crosses the midway circle. It's called the Yamyottara Vrutta or Dachinottara Vrutta or meridian in modern astronomy. Okay. How much time? See that angle corresponding, that's called the hour angle. Okay. So theta is that. So then now he says that the Shanku is, or cos Z, the zenith distance of the sun, okay, is or cos delta into sin theta cos phi plus sin delta sin. Okay. So if you know the time, you can find out the shadow, okay, or the cos z. Okay. Then, so the algorithm itself incorporate the proof. The algorithm itself will tell you how it is calculated. Okay. So now this r cos z is called Mahashanku. But if Mahashanku is no time, which is essentially this, this angle, essentially sine, I can tell you basically the angle, related to the sun's motion. Okay, 360 degrees is 1 day. Okay, so in like that, if you find out the angle corresponding to that, then divide by 15. So divide by 6, that you will get a time in Gatika. Okay? So angle and Gatikas are related. Okay, so it can give you, and one can find out time from this z. This is called Mahashanku. This r cos z is called Mahashanku. Lower here. Mahashanku. And actual shadow, the next, Panchasiddhantika will do the exact. Next slide, please. Slide 26. Yeah, Mahashanku. Mahashanku is r cos z. So direct algorithm for Shanku, for time in Panchasiddhantika. You see. So what is happening is this. Okay. So what do you observe and how do you find the time, right? So now suppose this OX is the gnomon. You see, it is a vertical thing. OX. Okay. Sun is coming at an angle Z with respect to vertical. That is called the zenith distance. Okay. And is casting a shadow. Okay. OY is the shadow. Okay. OY is the shadow. So that is S, the shadow. Okay. So one can easily see that is 12 tan Z. If OX is 12, so this is 12 tan Z. Okay. So from this one can find out the time in Nadi. You have to come lower. Time in Nadi. I don't see the last bottommost part. Bottom part of the slide. Time in Nadi. So zenith distance is Z. Shadow is 12 tan Z. And he talks about first star sign, earth sign, and all that. You come a little down, then you can see the exact formula. Time in terms of the shadow. See, Z, 12 tan Z is known. So from that, R cos Z can be found out. So time in Nadi is to find arc of R cos Z by cos phi cos delta minus or plus the chara, charajya. You take that. So after subtracting or adding, you take the R. So then add and then to that add the arc of this charajya, or add or subtract. So that is the time. Okay, so it gives it directly in terms of this Z. So Z is formed from this 12 tan Z. You see the shadow. Okay. Then latitude you are supposed to know, and declination you are supposed to know. So this is how the algorithms are written in Indian text. I wanted to tell them. Okay. So you have moved far from this Arthashastra formula, you see, and there's some other formula in later text, you see. So you have moved far from that, and given exact formula for time from shadow, you see. So this is remarkable. There is nothing of equivalent in Greek tradition and all that. This formula is not. They may give the method. I don't deny it. Okay. So the computation of planetary positions. So ancient theories and Kepler. You see, Kepler's model was more than 50 years before Newtonian formulations. So it's a kinematical model that does not involve concept of force, acceleration, equation of motion, etc. See, and no gravitation theory and all that. See, that is one important thing you should know, because lot of things in astronomy used to be known without physics proper, force, acceleration, and all that, and quite accurately too. And Kepler can be the most accurate before Newton. So, in the geocentric framework, Sun moves around the Earth, and the geocentric longitude of Sun will be heliocentric longitude of Earth is by 180 degrees. Okay? So now, how did the Kepler model, one can find out the longitude is the correct model. How did the ancients cope with the motion of planets which are observed to be complex as groups of Earth? So even in ancient times, the predictions of planetary positions were fairly accurate, and this means that the ancient models were in some sense approximations to the Kepler model. That is why they work. See, that is why they could calculate various things, planetary positions, time, on various things, you see, even though they didn't know these laws of physics and so on. So two corrections are added to the planets to find out its actual position. Manda Samskara, it gives the non-uniformity of motion is taken into account. And Shigra Samskara, because actually planets move around the sun, but you are calculating from the earth. So to take that into account, Shigra Samskara was used, but they didn't state it like that. You see, in fact, Nilakanta Somyaji only stated it like that, but it is implicit. So implicit was there, otherwise it wouldn't have worked. So these Manda and Shigra corrections are some epicycle models are used, okay, and Shigra extra in the Shigra correction, the planet is moves effectively. Planet moves around the sun in eccentric orbit, and sun moves around the Earth. Okay, so I written it for interior and exterior planet. There are some they didn't state it like that. In fact, some alternative kinds of pictures were also there. You see, so but Nilakanta is the one who straightened it out. Okay, very clearly he said that. So this is the planetary model of Nilakanta Somayaji. Okay, in which the planets move around the sun. Okay, and sun moves around the Earth. Okay, so now Nilakanta's unified model of planetary system showing the planets moving in eccentric orbits around the mean sun, which itself orbits around the Earth. So this, I think, this figure was drawn long back by Professor Ram Subramaniam, common papers. Okay, so I am reproducing that. So this is the so from the time of calculations of Manda, Shigra, and all that without telling what it is. So here you have the unified model of Nilakanta. Of course, he made some other important change also. I can't describe it, because it's a little technical. How the correction is actually done for Mercury, Venus. They are interior planets. You see, their orbits are inside the Earth. Okay, so Earth's orbit. So all these things he has analyzed in detail and then only come to this kind of a model. So to put matters in perspective, there is a model of Nilakanta Somayaji, the 1500 CE, and heliocentric model of Copernicus was 1542 CE. And this celebrated model had some defects, even Copernicus model. Of course, it gave a model for the whole solar system with the correct inter ratios of distances, but equation of center for corrections to Mercury, Venus were wrongly applied to mean sun. I mean, wrong way of handling some correction to the interior planet, which is an important thing, and Nilakanta applied it correctly. So, from a geocentric point of view, you can say that the revised model of Nilakanta was better than that of Copernicus, which presented a picture of solar system to scale, the sun as the center, and Nilakanta's model is somewhat close to Tycho Brahe model, which came around 1580 CE, because even in Europe, they didn't accept Copernicus formula. You see, now of course we feel it somewhat odd, You have a model in which planets go around the sun and the whole thing goes around the Earth. You see, we find it artificial, but those days, sun, Earth is the center, and because that is where everything you are doing from. So it didn't look very artificial to them. So this was the Tycho Brahe model, and Nilakanta's model is somewhat similar to Tycho Brahe model, though arrived at some different considerations. I am not going into details of Tycho Brahe model. I mean, how exactly the corrections and all that. Probably he was not as correct as Nilakanta. So apart from this, of course, so there is some systematic treatment of Triprashna problems in Nilakanta Somyaji's Tantra Sangraha and Jeshtadeva's Yukti Bhasha. Okay, so see, there are in a celestial object S like sun. You see, there are 4 variables associated with the celestial body. Declination delta, how much it is departing from the equator. Our angle H, how much it is traveled from the meridian. Zenith distance, what is the arc between the object and the zenith, that is zenith distance, and azimuth, you see, how much deviation from the prime vertical, you see. in the vertical circle or samamandala, you see how much angle, that is called the azimuth in basically, you see. So Jigamsha, okay. And of course you have the latitude of the location, there are total 5. So Tantra Sangraha gives the algorithm for finding any 2 of them when other 3 are specific. So there are 5C2 or 10 problems. The algorithms are given in Tantra Sangraha in the section on Dasha Prashna, 10 problems, and the full derivations are given in Yuktivar. So this is the final kind of a systematization of spherical astronomy problem in Nilakanta Somyaji. So what I want to, I think it's time to next slide please. See, Indian astronomy was not static. Okay. So it is mainly algorithmic as far as main texts are concerned. As we already saw, we had the formula for the daytime, we had the formula from shadow from time, time from shadow. Study these things to some extent. Many of the major texts have been studied. So one has to, probably many more things are there. So that is the reason for making. We have to keep studying them, and we have to develop our own narrative. To use the modern phrase nowadays. See, so one has to evolve our own narrative to explain these things, what exactly happened, and not deviating from the text and all that, without exaggerations, without going into flights of imagination and fantasy. Lot of things are there which are which can be legitimately told off and which are very clearly stated. You can stick to them mostly. So in the context of planetary motion, Siddhanta Shiromani use a very different method, that rate of motion of planets, etc. And calculus ideas are also used. You see, many of the mathematical ideas developed in the context of astronomy. We already saw trigonometry. Calculus also was developed in the context of astronomy. So first in the context of how the 2 later parts of the Siddhantic tradition, where the ideas evolve continuously, and what is the nature of it, that is algorithmic tradition. What is the nature of explanations, like in commentaries and so on. So thanks a lot. So I conclude my talk now. So any comments can be made. Thank you.
Thank you, sir. Sir, there is a concept of Jya. It's a short form of Trijya, and it's also called as Jiva or Jiva. So
Yeah.
its association of the 2 terms is not very clear.
What is not clear?
Jya and Jiva. How both of them are connected?
How it is? How they are equivalent used? I don't know. Jya is some kind of a string kind of a thing, right? So it is related to string. Whereas Jiva, how it comes, I don't know. Maybe some other string.
Also derived out of it, out of Jiva, Jeva.
Yeah.
That's right.
Jiva, yeah.
One more thing, there is a term Parva, which contains 15 tithis. So is it
what is it?
Paksha? In one of your slides, there is Parva. The term Parva is
Parva,
yeah. Whether it means the Paksha?
That is half a lunar month.
Paksha, does it refers to Paksha?
Apaksha, yeah, Paksha, yeah. Shukla Paksha, Krishna Paksha, Parva, yeah, same thing.
Thank you, sir.